is better. Cool. Right, okay. Sorry, I'm in quite a rush this morning, so I didn't get things like that. So yeah, thanks for the intro. That isn't, my sister is awesome, still, like 10 years later. So I'm going to talk about JavaScript browser bits. I'm Ben, as you just mentioned. I'm a developer. I'm just trying to rebrand as an adventurer. I'm based in Oxford, not very far away from here. I do these things, I think: visualization, data, real-time performance, VR interactions, lists of words. I do quite a few other things, but I'm in a massive rush today because we've got to get through quite a lot, so I don't really have time to say that, but come and chat to me later. I'd love to chat. So what I'm going to cover today is how to handle binary data in JavaScript, specifically in a browser. And we're going to look across these three different things. We're going to look at image data, audio data, so waveforms, and network data, and how we can access, modify, and play with those kind of things in the browser. So before we get into the bits and pieces of that, I just want to give a quick overview of how you can handle this kind of data within a browser. So all three of those are backed by this idea of array buffer. Has anyone heard of an array buffer, out of interest? Cool, like about half the room. So this is basically just a binary blob of data. So a whole lot of ones and zeros, and it's interesting because it's not within the JavaScript engine stack. It's kind of separated from that. And this allows us to kind of store arbitrary binary data within the browser. But you can't access it directly. To do that, you've got a couple of ways. One is to use a Dataview. So this allows you to set particular offsets. Oh, I'll select that. So if I put this in here, what we can do is we can call a Dataview and set, so this is saying at 0 to 255, and you can see the buffer up above has updated with that. And I can set the third one there, and we're able to kind of modify the buffer in this way. And the Dataview gives us this kind of tool for setting bits in that kind of binary blob. And there's a ton of different methods on that. The more kind of common way of accessing this data is through a typed array. So if we have this here, this basically creates an array. Oh, not that. This creates an array-like object which references that buffer. So you can see in this array it's 48 items long. We've got a 255, a 255 that match these two. And what we can do is we can set array 8. So say if we were to set 1 to 42, you can see that that has updated that that buffer at that point. So it's kind of like, although it feels like an array, it's actually a buffer. And what's really cool is that we can have multiple arrays, typed arrays, pointing at the same buffer. So this is a 32-bit array. Sorry, I'll make this a bit bigger. And you can see that this only has 12 items because there's only 12 times 32 bits in this buffer. And the numbers are larger than the int 8 array, because that can only go up to 255. And what's interesting about this is we can do, if we were to fill that with OXF, then you can see the stride of that array is different from the int 8 array. So you're able to kind of access these binary objects in kind of various strides using typed arrays, and there's a few more ones available as well. Right. And nice thing, as I said, these kind of live outside the JS engine heap, so it's really performant, really cool. Right. The second thing we're going to talk about quickly is numbers. So in JavaScript, all numbers are represented as a 64-bit double precision floating point array, floating point number. So for that, you've got to assign the exponent is how big that number is or how small it is, and then the fraction is the value of that number. So every number you use, regardless of whether it looks like an integer, is actually a floating point number represented in the engine. And you can see this. If you type in 0.1 plus 0.2, you get 0.3 and a little bit, which is kind of nice. And this will happen across any JavaScript runtime that you use. And it's not a bug, it's just the way it's represented. And also, integers are represented in the same way. So this is a really interesting thing, which is you can't have this integer in JavaScript, right? So if I open up the console here and I type this in, it returns the one below it. So you get you type in that little number and you get the one below it. But what's really odd is you can have the one above it. So that's a bit of an odd one. This is like this number is one past the maximum safe integer. So even though it looks like you're using ints, you're actually using floats. And the JavaScript runtime kind of hides all that, which is cool. There is a way around this, which is to use any kind of binary operator on a number. So here we're ORing it with 0, and that converts it into a signed 32-bit integer using 2's complement, which it's a lot simpler. You've got the sign, and then you've got the value over here. So this happens if you use an OR. So a single bar is a logical OR, an AND, a single ampersand, logical NOT, exclusive OR, bit shifting right, and that's it. I originally had a slide for each one of these, but it started going really long, so took that out. You can use this for some interesting things like flags. So you can set several flags to being like 10100. I'm not going to speak binary anymore. But you can use this to kind of set multiple flags in the same value, which is used sometimes, but not very frequently. There's some other things you can do. It's like this is a really kind of weirdly efficient way of doing math floor, so for smaller numbers, and the number is a bit, it doesn't use up, it's kind of a hyper optimization that you'd never really use. This is a bit of a weird one as well. Logical NOT, -1 and 2's complement is a series of ones in binary. So if you logical NOT that, it becomes a series of zeros. So this basically, by logical NOTing the return value of index of, you get whether or not that string doesn't contain that word, which is like a total kind of crazy thing. And basically, if you ever use this, your future self is going to hate you. Yeah, use that to troll someone, but not properly. Right, okay, so that's the kind of basis of how we access binary data and numbers in JavaScript. That's all the stuff we can do. So we're going to get some data. First of all, we're going to do images. So an image is a series of pixels in a kind of XY format. And the way we think about this when we're handling it in the browser is an array of these pixel values, with each pixel having red, green, blue, and alpha channel. So this is basically 4 components per pixel, and each of those components goes from 0 to 255, which is an unsigned integer value. So if you're using a typed array, it's a uint8 array. This is what this feels like. This is a picture of my mum. She's called Jodie. She's wearing my sunglasses in this picture, but I'm cool with that. So what we want to do is we want to take this picture of my mum and pull out all the pixel values from it. So currently we've just got this HTML tag. How might we do this? So we want to get these raw pixel values. The most popular way of doing this is, easiest way to do this, is to create a canvas element and then draw that image to that canvas element, and then you can read back the pixels. And when you, so at the bottom line of this, you can see I'm setting the image data to the return value of that get image data on the context. So that gives us this object, which has that array that I mentioned, full of those values, and metadata for the width and height of that image. So this is what you get back from that canvas element. Once we've got that, we can shove it back in using a similar call. This writes image data object to the canvas. And we can mix this together, right? Like, so what we're doing here is we're pulling out that image data array, we're iterating through it, and then putting it back on the canvas. this is all the code you need for it. And what I can do here, so we're jumping every fourth component, which is every pixel value. And if I set the first pixel to 0, this is taking out all the red values. So you can see that's run through that image, pulled out those red values. If we were to set them to 255, that sets the red component of every pixel to the max. And we can kind of play around with that kind of stuff. We could set the blue component to that. And so we're able to kind of mash around with that data, write it back, and see the updated content. We can use multiple components together. So this one is setting the red component to the inverse of the green component, which looks like that, which is pretty gnarly. Again, it's just these are quite simple, efficient, fast operations because it's using a typed array underneath. Also, these are just numbers, right? Like, so they're not you can do whatever you want. You can pass them to whatever function you want. So here, if we pass it to math sign, then we get this kind of like cool effect of it being red at the bottom, up to blue at the top. If we change the parameters of that a little bit, you get these stripes. And yeah, you can just mess around with this a lot, which is kind of interesting. I like that one. So yeah, this is kind of mashing all three of those together, and we can get kind of more interesting effects that kind of go diagonally using that sign function. And you can do some really crazy stuff. Like I put this together, I don't really know what it does. It's got an exclusive OR in it, and it's multiplying the value of the other one. I don't know. But basically it looks like this. And I'm not quite sure how this works. I think this is JPEG artifacts that are getting pulled out by that, but I don't know. So yeah. So this is when I was talking about the strides of typed arrays. We can do something quite interesting with this, which is we can create a new typed array that points to the buffer of that first image data array that's got a 32-bit stride rather than an 8-bit stride. And this means that every item in that array references a single pixel rather than a component within a pixel. So we can do stuff like this. So we can fill every pixel with a particular value, and we're not having to iterate through and jump forward by 4 every time. We're dealing with the actual pixels. This one here, it's quite interesting. It sorts all the pixels by the blue value, which isn't that useful of a filter. As I mentioned before, with binary numbers you can do bit masking, shifting. This does that. So what we're doing is we're iterating through that longer strided array, and we can do an AND with the red. So this is pulling out all the red components, but we could do, I think, red or blue. So we're basically using like a logical operation, but by using these color variables, it kind of makes sense in real life as well as that. That was terribly explained. We can do this stuff. So yeah, that's the end of images. We can basically use Canvas TD, pull out the stuff, pull out pixels, write them back, and do any manipulations we want on those arrays. Next up, we've got audio. So audio is stuff that you can hear. So it's kind of changes in pressure in the air, and we represent that with a waveform. Generally, the way that we think of this in a browser is, so you've basically got a sample rate. So you might have heard of like sound being sampled at 44K or something. That is every 44,000 times every second, you're taking a slice, a sample of that waveform, and then getting the value out of that. Sometimes this creates interesting artifacts, and especially if it's like too low. I don't really know, but yeah. So that's the sample rate, and so we're catching samples every like little slice, and we basically have an array of those. And generally, when we're using them in browser, they range from 0 to 255, but you can also use floats, but this is easier. And yeah, that's what that data looks like and feels like. So in the web, in the browser, one way of pulling in audio files is to use an audio tag. So I've just basically included this Bach OGG file, and when you do that, you get this kind of playback button. And when we play this, we got some cool music. So this is playing directly through the browser. Like, so we've got no way of interrogating what those waveform values are. But we can do this by using the WebAudio API. So this is a really interesting, fun API because it feels quite different from any other browser API because you create an audio graph. So you create all these kind of components that hook together, and then you basically run data through it. And then, so here we've got media element source, so that can point to an HTML media element. And then we run that all the way through to a destination, which would be the speakers. And what happens when you attach an audio graph to this media element is that it won't just play straight through the browser, it will play through that audio graph instead, and it'll be muted through the browser. We've got this node in the middle, which is called an analyzer node. That's what it says. It allows you to take a look at that data while it's flowing through. So it doesn't actually interrupt the flow of data, but it allows you to interrogate it a little bit, which is what we want. There's a few other nodes, which I'll get to in a bit. You've got buffer source node, which allows you to push data into that audio graph, and a script processor node, which is slightly different from an analyzer node, because that allows you to intercept all incoming messages, samples, and do something with them, process them, and send a different output out. These are all the kind of points that you can push in or pull out data. I was really into circles when I drew this diagram. I was really getting into that. And yeah, we're gonna talk about a few of these. So this is the entire code for connecting to an HTML audio tag and joining that to an analyzer node. And then once we've done that, we can pull out our time data from that analyzer node by using these two functions. So getting time domain data and frequency data, and we'll have a look at both of those just now. So this audio tag is being piped through the WebAudio graph, and through the analyzer node, we're picking out this time domain data. Currently, it's on 128, which is like halfway between 0 and 255-ish. And that's it's kind of like steady state. But where we start putting audio through that graph, you can see it starting to react, and we're starting to get more fluctuations in it. Which is cool. So we're getting that data out. We've got like, I think, 2,048 different samples. It's kind of hard to see in this typed array view. So what we can do is we can just write some JavaScript to draw that on a canvas element. So there's a few more lines here. So basically, we pull out that data, iterate through it, draw a line, and that looks like this. So we're able to kind of grab that raw waveform data through that analyzer node and pick it up. You've kind of got to stop that song at the right time, or else it feels really odd. It's really awkward. Right, okay, so that was the time domain data, but also we've got this other function on the analyzer node which allows us to get frequency data. So this looks a little different. In its steady state, it is all zeros, so it's kind of like right along the bottom. And as we play that, they're moving, but not as rapidly as the previous one. So it's got a different kind of feel to the data. So when we pipe this through exactly the same code for plotting along a canvas, we get this. So what this is, this line along the bottom isn't a waveform, it's a Fourier transform of that waveform. So this is pulling out the frequencies and the intensity of each of those frequencies. This can all be really explained really well with the GIF that I forgot to put in. But basically, that frequency data you can use to kind of reconstruct the kind of average wave of that time sample. And yeah, it's a really useful tool for kind of like analyzing audio and pulling out data. Right, okay, so that's us. We've pulled out data from our audio graph. We can also use the audio graph to push in data. So there's a couple ways of doing this. Buffer source node is a kind of nice, clean, easy way. Script processor, you've got a few more options, and we'll get to that in a bit. This is what this looks like. So you can basically create an audio buffer and then access the channel data of that audio buffer. And once you've got that channel data, you've got a typed array, which we know about now. And here it's a float 32 array, so you can set it from, I don't know what the bounds are, but you can do some stuff with it. I think it's 0 to 1. So what we've got here is we've got our channel data. We can just iterate through that, and we can connect that to our audio graph. And then once we start it, the bottom line there, then that will just start running through alongside all the other audio. So here, what we've got is we can just set this to a random noise, and this will give us like a white noise kind of sound. So we're taking a random noise, minusing 0.5, so it's centered around 0. I'm not sure if that's necessary, but that sounds like this. And you can see if we put this multiplier up, it will be a bit louder. I think that's pretty much all we can do with that. So that's us generating white noise through a buffer node. We can use sine to create a kind of more smoother wave, which will sound a bit more nice. So when we play this, we've got this like just a kind of normal sine wave, and that creates a tone, which feels a bit more kind of like rounded. We can also combine two sine waves. So basically this is, you got a wave, and we've got a sine wave going along like this, and then we've got another sine wave that goes up like this. When we multiply them together, what's going to happen is it's going to ease in and then ease out using this multiplication here. So you can hear it's a bit more of a kind of nice note by combining those two things together. We can also choose frequency to be a random. So every time we do this, it will play that same thing, but with a randomized frequency of sine wave. Oh, that wasn't very nice. Sorry about that. And yeah, that still sounds quite like shallow and not very kind of hearty noise, I guess. So what we can do is we can do a tiny little trick here, which is to play frequencies that harmonize with that original frequency by just multiplying by 2 and 4. It's a bit hacky, but it works. And so we get a bit of a richer sound now. So it's more like a kind of synth. And you can hear that difference of those of generating those different waveforms. So that's how we can kind of put audio into our audio graph here. Cool. So I'm going to be really quick here. Right, okay, this is a very short one. Network. So basically, in a browser, most of your network is HTTP, unless you're using WebRTC and you've got data channels. I think. So that's basically always going to be text-based-ish initially. I should have, it doesn't matter. It's like you can basically, but then that could follow with binary data. And the way that we can access this, if we've got a remote server with a binary blob of data, we can call fetch on it and then do this array buffer call. And that will give us that data in that form that we're able to kind of like mess around with and do stuff with. The other way around, we can use fetch to post up a buffer or a typed array, whatever we want, and that's going to result in taking binary data from our browser into a backend server. We can also do this over WebSockets. So if you type set the binary type property of a WebSocket to array buffer, then every message that you get down will be, the data of that will be a buffer that you can use to pipe into whatever you want. And you can send buffers the other way when you set it up like this. Okay, cool. So that's how all the kind of data feels. What we're going to do is we're going to try and combine stuff. How long do you have for time? Have I, all right?
You're okay.
Cool, excellent. We're going to combine stuff with other stuff, which is where things get fun. So first of all, what we're going to do is we're going to combine audio data with an image data. So, like, can we take audio frequencies that we looked at before and convert that into an image data? Not really, I guess. They don't really fit too well. One's like quite a long thing. The other one's kind of square. So yeah, they're kind of like different shapes of data. But what we can do is we can align these. So we can take an image data that is the same width as the audio frequency data is long, and we can kind of like shove that on top. And then we can assign timestamps to each of this, each row in this image data here, and kind of match these up on those timestamps, like this. And what we're doing here is now when we play this, when I press play here, it's going to pipe that audio through the audio graph. We're going to take the analyzer node data and we're going to shove it in a image data that we talked about before, and see how that looks. Does anyone know how this might look? Good. It looks like this. So we've got this kind of, this represents frequencies going up and time going across the way. So what we've got is we've got a very rudimentary spectrograph. I need to go to the slides. So we've got a spectrograph to, you might have seen this on like TV shows about submarines, or basically whenever you're analyzing audio data, you kind of have this view of frequencies over time. And what's quite nice is this is the entire code of it. You know, like, so there's no libraries, no frameworks here. We just like pull out that raw data, shove it in a canvas, and it kind of works. And we've had to do no processing at all. We're taking stuff from one place, shoving it into another place, and it kind of just works. Though we can actually do a couple of tweaks to make this better. So the first one is the data density. So we've got this bit of a problem that we're not actually showing all the data of that audio frequencies. And the reason for this is that we've got our image components, and that aligns the components with frequencies, which means we lose 3/4 of the data. But we know this handy trick of using a 32-bit array, and that strides them appropriately by pixels. So now we've got frequencies mapped to pixels. The second problem is color utilizations. These are all gray, right? Most of them are kind of like gray or white. And that's because we're plotting colors against frequencies all in the same way. So basically, at any frequency, pretty much, this is going to result in around the same color. We can do something like this. So use some maths to make this a bit more easier to see a difference in the colors than values. And we can use all that stuff we talked about before about masking colors to generate a new color from these components. That works. And so basically what it boils down to is we go through all the frequencies, set the image data to a mapped color of that value. And that looks like this. So we can see a lot more data here. We're getting way more stuff through. And you can actually make out those kind of high points of that data, high points of those frequencies. Right, okay, one last thing. So we've talked about taking images and audio. How about we put network in there as well? We know how we can kind of like take an audio and like visualize it through the spectrograph. But what if we mix in stuff that is remote? So Nexmo is a pretty cool service that does this. You can talk, yeah, that's, they do cloud-based communications. I don't know how to describe you. Yeah, cool. Go and talk to Sam or anyone else. Have you got other people here?
Yeah, go upstairs.
Cool. Go upstairs and talk to people about Nexmo. Really cool service. This allows you to programmatically create phone calls, and one of their services is WebSocket endpoints. So what you might use this for is for routing phone data to your backend server, so you can analyze it, so you can pull out information from it. And this is what this generally looks like. So you've got your server, you've got the Nexmo open a WebSocket connection to your server. But what we can do is we can just proxy that straight back down to the browser. So we're basically dumbly passing on that WebSocket to a browser client, which allows us to do some stuff. This looks quite complicated, but it's not. So basically, we've got this WebSocket connection from our server. We pass this through an audio graph with get user media microphone input, passes through there, goes up the WebSocket, back down again, back into the audio graph. Easy. These things here, we're kind of resampling data, and we're able to capture this whole thing. The nice thing about graphs is it's really easy to abstract parts of a graph. So we can take out that entire part and just say, like, it's in and out. And that looks like this. So what we've got here is you can see on the right-hand side, left-hand side, you can see my voice. Yeah. So we're seeing that kind of like live graph of my voice. On the right-hand side, I've got this thing which I can call my mum. So what should be happening now is in a few minutes, my mum's phone will ring, and we'll pipe that back through our audio graph, and you should see her speaking on the other side, maybe. I don't know, she might be busy. She might be bored of her son. Oh, that looks like it might be connecting.
Hello, Ben.
Hi, Mama.
Hi.
Hey, how are you doing?
I'm fine. Just been for a fabulous walk in the fields.
Cool. Nice one. Yeah, I'm glad. I'm in Birmingham.
Are you walking in the field as well?
No, I'm like kind of the opposite of that. So yeah, no, but yeah, thanks. I don't know how to hang out, but I guess I'll see you later or whatever.
Well, you'll have to talk to me all day then.
Sorry?
You'll have to talk to me all day then if you.
Yeah, yeah, I guess. Yeah, that is yeah. That's cool, I guess. Okay, cool. Thanks. I'll yeah, catch you later.
Okay.
Right, bye.
Bye.
Oh. I can just refresh the page to hang up. So these are some of the things we've covered. Binary operators, typed arrays, array buffers, those different ways you can access audio files, network stuff. And what's kind of interesting about this is I haven't used a single library. We're able to conduct that entire phone call with my mum in the field, I think, without using any kind of frameworks or libraries. And the reason I think it's especially interesting is that if you are wanting to do any of this stuff, it doesn't matter what you're using. As long as you're using JavaScript, you have this ability to operate on binary data at quite a low level. And yeah, you can do whatever you want with that. So thank you very much. Cheers.